Pose with the bands. Pose with the pose with the pose with the bands. Pose with the pose with the pose with the bands. Pose with the bands. Pose with the bands.
Assalamu alaikum and a very good day to everyone. My name is Farida Hazira. My student number is 2023657042. Today I'm going to present a case study related to modern engineering systems, focusing on the application of time-varying electromagnetic fields and wave propagation in wireless sensor networks, WSNs, used in smart agriculture. As technology advances, many engineering systems now rely on wireless communication to transfer information quickly and efficiently. In smart agriculture, this becomes especially important because farmers need to monitor their fields in real time, without depending on wired systems. Wireless sensor networks and the Internet of Things, IoT, are two major technologies that use electromagnetic wave propagation to send data between devices. But as we will see in this case study, the outdoor environment creates many challenges for electromagnetic wave transmission. Now that I have introduced the topic, let's look more closely at how wireless sensor networks are used in smart agriculture. I will explain how they work and why they are important. These are networks of small, battery-powered sensors placed in the field to measure things like soil moisture, temperature, humidity, and crop health. The data collected is then sent wirelessly to a main hub or cloud server using radio frequency, RF, waves. In terms of electromagnetic theory, these radio waves are time-varying fields that travel through the air, but their strength can be affected by obstacles, weather, and soil conditions. WSNs help farmers in many ways by providing real-time updates for irrigation control, helping to detect plant diseases early, and supporting automated farming with drones and machinery. All of this contributes to more sustainable food production, reduced costs, and less resource waste. However, all of these benefits depend on reliable signal transmission, which brings us to our electromagnetic wave challenges. From our study, we came up with two main research questions. 1. To study how outdoor environments, such as rain, vegetation, or terrain, affect the strength and behavior of electromagnetic waves used in WSNs. We want to know how these factors cause weak signals, reflections, or blockages. 2. To find out what methods or technologies can improve communication in tough environments. This might include better antenna placement, stronger signals, choosing the right frequency, or using advanced techniques to reduce signal errors. Let's look at the problem statement for our study. Wireless sensor networks are very helpful in agriculture, but they face several real-world issues. The main problem we identified is that wireless sensor networks often face signal issues due to the changing outdoor environment. As crops grow, the signal path is blocked. Soil moisture can weaken the signal. Trees and farm buildings can cause reflections or scattering. If the signal is too weak or gets blocked, the system fails to send data on time, which means farmers might miss the chance to water or fertilize at the right moment. Also, if antennas are placed too low or the frequency is not suitable, the signals may be absorbed by the soil or blocked by tall plants. So even though wireless sensor networks are designed for the outdoors, real-world environments create communication problems that affect smart farming performance. Solving this is key to making sure smart agriculture continues to grow. So that's how WSNs help farmers collect data from the field. Next, let's move on to the Internet of Things, or IoT, which connects all the smart devices together. IoT is a bigger system that includes wireless sensor networks and connects them with other smart devices, like weather sensors, drones, and even mobile phones. What makes IoT powerful is that all these devices can share information and work together. For example, data collected from the field can be sent to the cloud, where it's stored and analyzed. Farmers can then use that information to make better decisions, and they can even control systems like irrigation remotely using a smartphone. So basically, wireless sensor networks gather the data, and IoT handles the communication and control. Together, they help farmers respond faster to environmental changes, improve crop quality, and reduce waste. Now that we understand how wireless sensor networks and IoT work together, let's look at another advanced technology, underwater wireless sensor networks, or UWSNs, which are used in water-based farming systems. Besides traditional field sensors, smart agriculture also uses underwater wireless sensor networks, UWSNs, especially in systems like aquaculture, hydroponics, and paddy fields. These underwater wireless sensor networks, UWSNs, operate below water, collecting information such as water temperature, pH levels, turbidity, dissolved oxygen, and nutrient concentration. This data is transmitted wirelessly to surface receivers using acoustic or electromagnetic waves, depending on the setup. Underwater wireless sensor networks, UWSNs, use sensor nodes to measure water parameters such as temperature, pH, turbidity, dissolved oxygen, and nutrients. This data is sent wirelessly to the surface or a server, so farmers can monitor water conditions in real time. They reduce labor, improve efficiency, and can even be linked to IoT systems to automate things like water levels or oxygen supply. They can also be integrated with IoT systems, so automatic controls, like aeration or nutrient dosing, can be activated based on the data collected. For example, in paddy farming, these sensors can help maintain the best water level or acidity for rice. And in fish farming, they make sure oxygen levels are safe. It's a smart, hands-free way to protect water-based agriculture. That's all from me. I will now pass to Adil Farkley, who will continue with the next part of our presentation.
On to the second chapter. Background on electromagnetic wave propagation. Electromagnetic wave propagation refers to the movement of electromagnetic energy through a medium or vacuum. It is governed by Maxwell's equation, which explain how electric and magnetic fields are generated and interact. Faraday's law states that a changing magnetic field produces an electric field. This interaction is essential in forming electromagnetic wave. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. This continuous cycle allows electromagnetic wave to propagate through space without needing a physical medium. This is equation 1. Faraday's law of electromagnetic induction. A changing magnetic field B over time creates a circulating electric field E. This is one of the Maxwell equations showing how time-varying magnetic fields induce electric field. It explains how electromagnetic waves begin to form. This is equation 2, wave equation for electromagnetic wave. These are wave equations for the electric field E and magnetic field B. They show that both fields propagate as waves in space. There are 5 applications in wireless sensor network in smart agriculture. First is remote sensing for crop monitoring. Satellite or drone-based sensors use electromagnetic wave to monitor crop health, growth pattern, and vegetation indices. Second, soil moisture detection. Microwave and radar-based sensors are used to detect soil moisture level, helping in precision irrigation and water management. Third is wireless sensor network. Electromagnetic wave-based communication connects soil temperature, humidity, and light sensor across the farm. Fourth is automated irrigation system. This system uses electromagnetic wave to transmit data from sensor to controller, allowing real-time irrigation based on soil and weather condition. Fifth is weather forecasting and climate monitoring. Electromagnetic wave data from satellite is used to predict rainfall, temperature, and climate patterns, helping farmers make timely decisions.
Next, we go to the role of electromagnetic wave propagation in smart agriculture. So, electromagnetic wave plays a vital role in the development and operation of smart agriculture system, which is its EM wave is integrated to increase productivity, resource efficiency, and sustainability. Also, EM wave leverage wireless communication, remote sensing, and also integration of automation technologies in smart agriculture system. As for example, is weather communication, TDR sensing, subsurface comm, and UAV integration. So we will go one by one the role of EM wave in smart agriculture, which is enabling wireless communication in the agriculture field. It is a backbone of smart agriculture. It is used for measure soil moisture, temperature, humidity, pH level, and pest activity. Second, soil and crop monitoring via EM-based sensing. First, EM wave also contribute to the time domain reflectometry (TDR) and frequency domain reflectometry (FDR). Is used to measure parameters like volumetric water content and salinity, and also soil texture. Third is EM propagation for subsurface and in-canopy communication. It is involved wireless data exchange within the plant canopy or underground sensors. It uses lower frequency, lower than 500 MHz for subsurface comms that are effective due to lower attenuation in moist and compacted soil, and sub-gigahertz offers better propagation through foliage and longer range with lower power for in-canopy communication. And lastly is integration with intelligent system and UAV. Recent advancement in smart farming involved with edge computing and unmanned aerial vehicle UAVs. UAVs equipped with multi-band antennas and sensors that can collect high-resolution data on crop health, soil moisture, and terrain mapping using spectral and EM reflectance data.
Next, I will tell you about environmental effect on electromagnetic wave propagation. Okay, the first one is moisture in soil and air. The presence of moisture in both soil and air significantly affect electromagnetic wave propagation by absorbing and scattering signals, particularly at higher frequencies above 1 GHz, resulting in weaker and less reliable communication during rain, irrigation, or humid weather conditions. If you can see in the picture, the electromagnetic wave produced can have a bad effect on plant and also on the growth of metabolism. I will continue with the second point, which is rain weakness high frequency signals. Rain causes signals scattering and absorption, especially at frequencies above 1 GHz, leading to reduced signal strength and communication reliability. As in the picture shown, you can see that there are several electromagnetic waves that can have a bad effect on the Earth's atmosphere, and also it can thin the Earth's layer and cause the Earth to become hotter. The third point is that vegetation can block, absorb, or scatter electromagnetic signals in smart agriculture system. While crop are the primary target for monitoring, they can interfere with wireless communication. Dense or water-rich plants, such as those in corn or sugarcane fields, can absorb the scattered signals, causing signals loss, reflection, or multipart fading. This effect reduces the accuracy and stability of data transmission. Therefore, vegetation density and moisture must be taken into account when designing sensor networks to maintain reliable communication in the field. The last point is that man-made structures and moving machinery can block, reflect, interfere with electromagnetic signals in agricultural environments. Structures like greenhouse, metal fence, and storage buildings, as well as mobile equipment such as tractors and drones, can reflect or obstruct wireless signals, leading to interference or signal fading. This disruption reduces communication reliable in smart farming systems. To overcome these issues, systems should be carefully designed by selecting appropriate frequencies, positioning antennas to avoid obstacles, and applying error correction techniques. Recognizing these challenges is essential for developing durable and dependable wireless sensor networks suited for real-world agricultural use.
Smart agriculture communication technologies. Smart agriculture depends heavily on reliable wireless sensor networks, or WSNS, to deliver real-time data across the farm. But these networks face challenges. Signal strength can be weakened by vegetation, soil moisture, and terrain variations. To address this, Fujitsu Japan's Akasoi platform incorporates several key technologies. One of the most important is LoRaWAN, or Long Range, Low Power Wireless Communication System. It's ideal for large farms, allowing sensors to transmit over several kilometers while consuming very little energy. To improve reliability, mesh networking is also used. This creates a web of connections where each node can relay data through multiple paths. So, if one path fails due to interference or damage, the system automatically reroutes the data in a self-healing design that keeps the network functional. Fujitsu also adds intelligence to the network with the AI-powered cloud processing. Data from sensors is analyzed in real time, enabling automated responses like adjusting irrigation levels or greenhouse ventilation without human input. Finally, adaptive frequency switching allows the system to automatically change to better frequency bands when interference from fog, rain, or dense crops occurs. This ensures more stable and reliable signal transmission. Next, sustainable and efficient network operation. In addition to strong communication, sustainability and efficiency are built into the design. Many sensor nodes are solar-powered, reducing dependence on external power sources. These devices also operate on low-duty cycles, meaning they only activate at scheduled times. This conserves energy and significantly extends battery life, cutting down on maintenance needs. When combined, these technologies offer long-range data transmission, even in rural or hard-to-reach areas, network redundancy through mesh-based routing, and automation and adaptability thanks to AI and frequency control. The result is a robust, low-maintenance communication system that can withstand the demands of dynamic, outdoor farming environments.